Start very simple. Sorry to disappoint a little bit. I will not talk too much about disasters, but more about nightmares. My personal nightmare of securing a multi-purpose computer center, and not to spoil the result, but actually still I might do. I don't have answers. I have a question, and maybe some of the participants here are running computer centers and help me later on to solve those questions. So maybe just a small sign with your hands in the participants. Somebody running a computer center here? Okay, let's see then. Maybe you come up later and we'll figure out where my problems are. Maybe you still get some answers to my problems. So I will talk about the nightmare of securing a multi-purpose computer center. I will give a very short introduction to CERN for those who didn't follow my first lectures, and then I will also talk a little bit about our computer center so you get an idea what I'm talking about, and then we'll delve directly into the problems in securing this beast and or the problems of not being able to secure that beast. So about CERN, just one step back. Some of you might have seen this brilliant pictures from the Webb Space Telescope looking back into the universe close to the Big Bang. That is one way to do, looking for the light which is coming from the Big Bang 13.7 billion years ago. At CERN, we do this differently. We try to reproduce the conditions, something like in nanoseconds after the Big Bang, but we do this, of course, locally here on planet Earth. So question is, what was the state of matter after the Big Bang? So what happened at the time? What were the laws of Mother Nature? How did this all function out? What is the universe mass made of? Because if you look in the sky, what you see is only 5% of the mass of the universe. There's another 20 to 25%, which is actually mass generating gravity, like galaxies, sun, stars, and planets. On the other hand, there's another 70 to 75% of dark energy, which we have no clue what it is. Of course, there are theories, but apart from seeing evidence that there must be something like that dark energy, we have no clue how this fits into the theory. And last but not least, since we all believe in balances, where money is debt, and where matter is antimatter, but we do not see any antimatter in this universe. And I can prove this to you. If there is something like half of the universe full of antimatter, where antimatter and matter meet, where they hit each other, this is the moment where there's an annihilation which is producing light. So tonight, look in your sky, and if you see somewhere a huge wall of light, this is then where antimatter and matter are hitting. And since you had a look before, I guess, you figure out there is no wall of light in the universe, which means there is no huge realm of antimatter where there's an anti-Earth, an anti-Sun, and anti-Milky Way. This is just not existing. The universe is void of antimatter, and nearly, and the rest what's left over, it's matter. So why is that? Why is this imbalance there? So in order to figure this out, what we do is we do the brutal way. We try to produce conditions, energy densities, which are more or less something like in nanoseconds after the Big Bang. How to do this is very simple. If you want to look at your mobile phone, take your mobile phone now in the hand and smack it against the wall. And if you smack it hard enough, then you overcome the electric force, which is more or less just repelling your mobile phone from the wall, but it's really then disintegrating because you smacked it very hard. You can look in the interior of the mobile phone, and this gives you a first glimpse on how your mobile phone might work. Of course, you can do this once, because once you smacked it, it's damaged. We get protons, we get zillions of protons, so we get it much easier. We take two protons, we smack them together. When we smack them together, we produce energy on the spot for Mother Nature. To increase our chances, we put the protons into something we call bunches. So there's something 100 billion protons per bunch, and we cross the bunches. And this is like two groups of football fans crossing each other, and some will hit each other, not hitly in the violent way, but because just too much people in the space, yeah, people will hit each other. And the same is happening here. You get the two bunches, they cross each other, and when the bunches cross each other, then you get collisions. In order to do this repetitively, we put the bunches into beams. They get two beams. We colorize them with red and blue. Actually, they don't have any color, but for illustration purposes, we gave them blue and red color. And each beam is consisting of about 2,822 bunches, just put up as a train with lots and lots of wagons. So those two beams are kept separately all over the circumference of the accelerator. And only in 4 collision points, we cross the beams. I know you shouldn't do this. I've seen Ghostbusters, as you might have seen it, but still we cross the beams, and when we're crossing the beams, the bunches penetrate each other, and when they penetrate each other, Protons find a partner, collide, and when they collide with such an energy that the energy density is close to that 1 nanosecond after the Big Bang. For this, you need to have a very, very big accelerator because you would like to get them on maximum speed. The speed more or less is proportional to the radius of your accelerator. And so this is how the accelerator is looking like. You see already the tunnel is more or less straight. It has a curvature. You can see the very end of this picture. On the right-hand side, you can see the end of the picture. You can see the white line, which is there for our trains in the tunnel, which have cameras to follow this white line for transport. And some nasty people say this white line is also for our French colleagues to find the way out if they have once they have drunk too much wine. On the left-hand side, you see the assembly of those accelerator components. The blue tube, this is called a dipole magnet, a two-pole magnet with north and south pole. The north and south makes two. And those are just the rails to guide the beams. And the beams are the small, little, tiny beam pipe, which you can see in the very center. I marked again the red and the blue beams, so they're kept separate. You see the beam pipe around, you see some copper collars, which is more or less the magnet to keep the beam on a circular path. And everything else is a huge assembly of a cryo plant. It's a fridge, because the current need to keep those beams on the trajectory is something like 11,000 amps. So it's something like 1,000 times the current you get out of your socket at home. 11,000 amps, that's the maximum we can do with the material we're using. And even for this, we need to use superconducting cables. So this means that the whole assembly here, the whole accelerator, 27 kilometers long, is cooled down to 1.9 degrees Kelvin or minus 271 degrees Celsius. And please, somebody help me with Fahrenheit. I have no clue how much is in Fahrenheit. I would guess 400 and minus 480, but I might be completely off there. So maybe somebody can put this in the chat. I would love to learn how much it is. Of course, I can calculate myself.
Doesn't even matter.
Doesn't even matter, but it's damn cold. So it's even colder than in the Canadian winter. And I think we agree that is even damn cold. So we can even do colder. And the superconductivity we need to have, because the material which is used for the superconducting cable needs to be kept cold. Only when it's kept cold, it can bear the 11,000 amps current. But if it's getting too warm, talking about 4 Kelvin or even 10 Kelvin, then the superconductivity is lost, and we might have a threat to our accelerator. Threat to the accelerator, getting an idea of the beam size. I took here now the €1 coin. You might have seen it. If you watch at Spain, close to the right end of the one, Spain is 4 millimeters on the euro coin. That is more or less the beam size. And if you not look at safety, the stored energy in each of the beam corresponds to 80 kilograms of TNT, but of the size of Spain. So 4 millimeters distributed over 27 kilometers accelerator tunnel. That is more or less the same energy a Boeing 747 has when it's at V rotation. So when it's just starting to rotate to lift off of the runway. And but the Boeing is much, much larger compared to this tiny beam. So, but it gives an idea how much energy there is. And as I've explained in other presentations earlier, we have lots of safety systems in place to make sure that the beam stays within the aperture of the vacuum beam pipe and is not hitting the beam pipe, nor the magnet, nor even the tunnel, because when it will do, it will be more or less a Star Wars laser, Jedi laser lightsaber, and more or less destroy part of the accelerator. This is where I'm living. On the right-hand side, you can see, top right, you see the Lake Geneva. You see the airport on the right-hand side. You see the big circle. That is the Large Hadron Collider. It has 27 kilometer circumference, and the accelerator is something like 140 meters underground. So it's a little bit tilted. It's not horizontally put in because of the earth material where we dug the tunnel in. It is also not horizontal, so we needed to make some compromises. The beams are circulating in this accelerator with something like 11,000 turns a second. And as I said, the 2,822 bunches have a distance between each other about 25 nanoseconds. This number will come back later. So, and in 4 collision points around the circumference of the accelerator, we put something we call experiments, something like photo cameras where we cross the beams. And then every time, every 25 nanoseconds, when there is a beam crossing, we take a picture. And this is more or less looking like this. So here we got the Atlas camera, Atlas detector. Just for the scale, there's a small foreman which is working in this experiment, and this is how the experiment was looking like when it was in construction in 2004. This is how it's looking now in open state. You still see a small guy working at the bottom of the pit. To give you an idea, the experiment is something like 43 meters long and 25 meters in diameter. Think of your Nokia or your Nikon or Canon or whatever. camera you got. This is the same thing. Functionality is similar, but of course the scale is much, much bigger because the collisions are very, very energetic, and you need to absorb everything what's coming from the collision. This is a photo of a collision. You see the red and the blue. Oh, sorry, too fast. Red and blue beam coming in, and the first thing you can see, you see the assembly of the detector. So in the middle of the detector, you got the collision, and you see the end product. You do not get a film of the collision. You just see what's coming out of collision, which is on the top right. That's the view perpendicular to the beam line. You see there are lots and lots of secondary particles which are produced in the collision. So it's your telephone again. It is one entity which you get it here. Once you smack it into the wall, and you get lots of different parts, and the different parts we got here. So we got some chips and some screens and some buttons and some diodes and so on. And here it is more simple. It's protons, neutrons, pions, and what else is coming out. And on the top left, on the bottom left, what you can see is there's not even one collision. You see all those shiny little dots along the horizontal line. We got usually something like between 20 and 40 protons which find a partner. So every photo we're taking, every 25 nanoseconds, you got an overlay of something like 20 to 40 collisions. And then by digital means, you have to separate this. Here's another camera again for the scale. I put a standard electronics cabinet on the left, top left of the picture. That is pure electronics. What you see here, you watch directly into the beam line of the experiment. Obviously, there is no beam line yet because that is still in the construction. On the right-hand picture, you see that one of the slices of this detector, where all the slices have been assembled on surface, is brought down by a huge crane over the 120 meters to the shaft, into the tunnel. So the weight of this particular piece is about 1,200 tons. The heaviest one was 2,500 tons. And here's another collision. I'm a little bit off with my beam there. It should be a little bit lower, but you get an idea where the collision is happening. So we get 25 million bunch crossings. That is just the calculation out of the 25 nanoseconds. Between 10 and 40 collisions per crossing, which means we have with 10 megabytes of photo size, something like 1 petabyte of raw data. That is in principle what is produced in the experiments, in each of the 4 experiments, which is then filtered down. And here we're hitting the first time computer centers. Each of the experiments have a local computer center, which is hosting about 2,000 to 3,000 data acquisition servers, which are just used to take the picture, reduce the picture, and filter this down to a stream of between 10 and 20 gigabit per second, which we then really can harvest with the main computer center. So this means we have to throw away a very large fraction of the pictures. But again, this is close to reality. Think yourself going to Disneyland. You're not taking pictures of everything, don't you? You're just taking pictures of the interesting thing. And the same thing is happening here. You look what you would like to take a picture of, and when it's interesting, for example, you see a family and you take your camera out, you take a picture. And the same is happening here. We got the collision, and then there are some algorithms which are automatically deciding within 25 nanoseconds, is this something we'd like to keep? Is this your family? Or is this another family which we do not want to keep? We don't take a picture of that one. And then with this, we can reduce this down to something like 40 petabytes of data a year. So that's a filtering mechanism. We call this a trigger mechanism to figure out which picture we'd like to trigger on and which we'd like to disregard. Here's the computer center. So we're doing worldwide data processing. The computer center is more or less at CERN, is absorbing the whole stream of all this data into the computer center as something as a top node. We call this the tier 0 node. We run something like 450,000 CPU cores in the computer center at CERN, and we have something like 330 plus 400 petabytes stored on hard disks and on tape. For compute, we have an Instagram for physicists. We call this the Worldwide Large Hadron Colliders Computing Grid, the WLCG, and we distribute the data. This 40 petabyte of data produced per year, the 400 petabytes, which I mentioned here on the slide, we distribute this over computer centers around the world. If you want to see the data, the closest to you is, I guess, I think it's still Vancouver. So head over to Vancouver. It has a physics lab called Triumph, and they are part of the so-called tier 1. That is the second layer where we distribute the data. So there are 150 computer centers distributed worldwide, and in total we have something like 900,000 CPU cores as a compute for physicists. So they can log into this one like Instagram and say, look here, give me all the collisions being taken on the 15th of July 2022 with the Atlas experiments, and then there's some compute going on, and after a while you're getting all your results. So the slide saying we got 300,000 concurrent analysis jobs at this moment being processed in this worldwide grid, and the throughput over the planet is something like 60 gigabytes per second. So this is then how it's looking like in an animation. This is what the return on investment is looking like. You got in red the theory of the theoretical prediction of the theorists. And if you look close, you can see how the data is popping in between November 2011 and December 2012, our first run of data. And you see there's a discrepancy between the expectation of the theorists and the measurement. This is now marked here in blue. And this is what a signal looks like. This is when you process millions and millions and millions of those data. I'm talking about this 40 to 80 petabytes for this course of the 2 years. And in the end, return on investment is the Nobel Prize for François Englert and Peter W. Higgs, which was just attributed 10 years and 1 week ago. And on the other hand, this gives no insight into how Mother Nature is ticking, what the rules of Mother Nature's are. So, but coming back to computer centers, CERN's main computer center on the top left, you got the picture of this computer center once more. Now going to computer center security. This is how a computer center is looking like. Lots and lots of ALs with lots and lots of hardware. We are running 6 computer centers at CERN, which are serving, this is now where my dilemma is starting, different communities, but different overlapping communities. Of course, it's the Instagram, so the compute and storage of all the physics data. On the other hand, running an accelerator, running an experiment, running our infrastructure, you need to have a computer center. Look at your digital camera once more. It has a small storage space inside the chip, which is taking all the pictures. And we just got this in big. You get some control systems to run accelerators, control systems to run experiments, and then we get a worldwide user community, not only on the CERN side, which is the bottom left picture where you see the physics side, the laboratory of CERN. You see further away my house and the Jura Mountain. And if you now would like turn 108, you will see the Lake Geneva, unfortunately, not on the picture. We serve our user community because they need lots and lots of different software packages. So the computer center at CERN is doing compute and storage for data analysis, serving control systems for accelerators and experiments, but also providing operating systems to our constituency. You want to have a Windows installation, you would like to have a Linux installation. There you go, you get it from the IT department of CERN out of their computer center. Antivirus software, there you go. Want to print something? Yes, paper still existing. Printing service, IT department, data center. If you need to have a Word, Office Word, Office Excel, PowerPoint, any other engineering application, Mathematica, MathCAD, COMSOL, ANSYS, HR applications, finance applications coming out of the computer center, being provided from there. Collaboration tools like Zoom, but also for video conferencing, for audio conferencing, it's all coming out of the computer center. Web services. To serve our user community, we have a plethora of web pages being displayed to the world. If you go to CERN.ch, if you Google for CERN.ch, you might see some of them. In total, we have something like 15,000 web pages. CERN.ch/security is one of those, but hosting behind is 1.5 million web pages. So this is what we have to take care out of the computer center. And some of the web pages are used to display control system statuses to the control system engineers. At the same time, it's displayed in the offices because some of the engineers might sit somewhere in the office and work from there. And last but not least, you would like to display some statuses to the world. There are some web pages which display in which state the Large Hadron Collider at this very moment is. So you see it's already starting a little bit, getting a little bit fuzzy. Of course, we provide networking, we provide telephony, we have the CERN Internet Exchange Point in our data center, which is serving like 10% of the whole bandwidth of Switzerland, which is going to Switzerland internet service providers. We have a database on demand service with a couple of thousands of databases being ready for our users. Storage, I mentioned, of course, backups for disaster recovery. And then if you are in programming, I don't know if you are, but if you're doing programming, you need a versioning system like Git, GitLab, build systems, you need to have ticketing system, Jira, and then of course we'd like to have a virtualization service to run your developments or even containers, which is leading us to the problem of the presentation here, and in principle to why this is a nightmare. Because if you look at security risks, the world is not getting easier. There are more and more threats towards our digital infrastructure. It will not go away, and we have to face this. But those hackers, those attackers will not just go and say, look here, oh, done now cyber, let's go to something else. I think for the moment this will not happen until we get a huge revolution in technology. But for the moment, there are more and more adversaries against data centers. Ransomware attacks against hospitals, against data centers, against universities that have been seen in the past. This will not go away. Complexity, we'll talk about this in a second because this is where my nightmare starts. In the past, our systems have been more simple. It's getting more and more complex. If you're running control systems, in the past, you had a loop, you had some sensors, you had some actuators, and you had some controllers, and that's it. And then the SCADA systems came up, and you put some like visualization in a central control room on top of that. And then you get remote maintenance. So now you have to open it to the internet because the guys from Honeywell or Siemens or ABB or wherever they are, they would like to access your control system over the distance. Shit, now you get a real problem because they need your remote access and you add more and more layers to your control system. At CERN, in the past, we're running dedicated control system isolated. Nowadays, the control system are running in the same virtual environment, the same control system environment, the same container environment as we do for IT applications. And that means also that the consequences and the dependencies are on the rise. So it is not going down. So let's have a look at a computer center, the computer center mantras. The very first thing is convenient, cheap, secure. And you just pick two because you just can pick two. They are not consistent with each other. You just have to pick. Yeah, you want to have it cheap, it cannot be secure. You want to have it secure, you have to invest money. So it's not working. So this is why security is losing. We do not bring any immediate benefits. We are just a cost factor, and that's the sad truth which is there. But yeah, that's my life. Then the next mantra is keep it simple, stupid. But if you look at our world today, it is far away from being simple. Look at your car. Don't know which car you're running. If you have a very old Volkswagen Beetle, for example, you can repair it yourself. If you buy now a modern car, can you still repair it? If you can, you're really good. Mostly you can't because cars are getting more complicated. Mobile phones are getting more complicated because now you get all the apps installed. You need to have a cloud service somewhere which is delivering you with all the apps and all the backups. Think of buying. You just don't take your dollar out anymore for paying. You need to have the infrastructure of credit cards and everything behind. So everything like credit cards behind. So all the networking to connect directly to the bank. So we have overcomplication. Sorry.
So Stefan, on the note there of cloud services, Mary was asking what cloud services you are using.
We don't. So our computer center has 10,000 servers. We run our own virtualization private public cloud inside based on OpenStack. So yes, we're using some cloud service for dedicated purposes. So ServiceNow, for example, for ticketing, Sunroof for user interview for HR. But at the moment, the only cloud we're using is the Worldwide Computing Grid, which is again a dedicated cloud. And in principle, our term of grid was even there before. Because we call it grid because the computer centers for the worldwide grid are more or less available like the electricity grid is. Later on, the term cloud has been termed, but what I showed you before with this worldwide network, this is more or less a cloud service where you get lots and lots of computer centers serving for the compute. But apart from this one, we are not using any cloud service. There is a tendency to maybe consider to use Microsoft Cloud for certain Office applications like Outlook, and there's a tendency using Google Workspace for the Linux community for shared documentation, but our core infrastructure still stays on site. I hope this is answering your question. If not, are we still self-sufficient? To a certain extent, we are, Mary. There are, of course, limits, and costs also drives us to go more and more on the cloud. I'm personally not completely convinced that the cloud is the right answer to save costs. Short term, definitely not. Long term, you got the vendor lock-in, and once you're locked in the vendor, then he might start and spiral up the costs. So I'm not completely convinced. On the other hand, I would like to, I would like to keep everything still on site. So having an internal or private cloud. But we can discuss this later if you want to. Happy to talk. Let's come back to the computer center. If you just look at the complexity of today's infrastructure, and I'll give you an example in a second, this makes a security nightmare. And this is why technically I'm still sleeping well, but this is where I got a problem. Then there's defense in depth. You need to protect means on every layer, on the hardware layer, on the software stack, and so on. So having agile and timely updating. But this fails already with control system. For those here who are running control systems, you might lose your certification. You might need to recertify your whole control system. Are you really sure that your safety systems are still working? So agile and timely updating works, maybe, but not always. Then you need to have a secure professional software development. But hand to your heart, if you're under time pressure, you don't do this. You just download some libraries and packages from the internet. You use them and you do not check whether they are sober and clean and can be used. And about training and documentation, I think we all have seen code which is definitely written by untrained security developers, and I have lots and lots of physicists who are untrained security software developers, and there's also lots of stuff which is not deployed, not documented. Then tested business continuity plans. At least this is something which we are doing, and we can. And then we got logging and IDS. Unfortunately, this is in my hand, so I think we're not doing too bad. But this is where defense in depth comes in. Network segregation, compartmentalization, firewalls, busting holes, gateways, proxies. Let's have a look why I have a nightmare, because they don't work anymore. And I'll explain to you why. So I do not have the ultimate truth. I understand this problem partly to 100%. I got a good idea, and there are lots of discussions going on how we can optimize this. So one other disclaimer before I go on the detail. I will not discuss any best practices of securing hardware or software components themselves. So there's vulnerability management and patching, business continuity, disaster recovery, secure software development, input sanitization, filtering, also, and access control. I will not discuss any of them. I will just look at the network basis. So let's go to the meat. Here's my hardware. Introduction of a server. I got some hardware here. And in the past, on top of this hardware was the operating system. Brilliant. So I had to secure the BIOS, the IP&I interface to the hardware, which I can put on a network. I got the operating system. There are means for patching the operating system. And I got my guest book. I take it as an example here, a web-based guest book, which is just a web application written by some physicist or some computer engineer. 1, 2, 3 layers. Brilliant. This is something I was used to secure in the 2010. But nowadays it changed, and this is where my nightmare is starting. I got more hardware and IPMI and BMC, and nowadays the BMC is running a full-blown operating system. Think of Heartbleed. Now you have to patch your firmware. It's not something which is statically burned into the BIOS. Now it's something which you can update, which is huge, which is rather flexible. It might even be based on some kind of derivative of Linux. So now you have to apply the full updating mechanisms for your Linux BMC BIOS system. I don't have an operating system anymore. I got now something bigger called a hypervisor, because we all love virtual machines. So here's my operating system. Now that's snuck already one layer more in. Instead of having 2 layers, hardware and operating system, I got now hardware, hypervisor, and virtual machine or operating system. So I have 1 layer more to secure, and there is my guest book. Fair. Okay, 1 layer more. But no, there are more virtual machines running on the same hypervisor. So now, and we've seen this in the past, the hypervisor is just your hardware. So if you can break out of one virtual machine, you might be able, via the hypervisor, break into the other virtual machines. So now you got something which is even where intrusion detection is getting more and more complicated. Before you can do this on network level. Now this is more on the chipset level, on the motherboard level, into the hypervisor. So there might be completely different services running in the virtual machine. So one service might be used for control system, and the other might be a public web page, while the third virtual machine is run for finance and HR. Of course, you can now introduce segmentation, saying, look here, there's a HR cluster, and there's a control system cluster, and there is the finance cluster, but that will give you away all the agility, all the flexibility, which you would like to gain. So instead of, you pull everything together. So full separation will kill this elasticity of your virtualization cluster, because you would like to see it growing and using the virtual machines for whatever purpose you got. And then there are containers, and my nightmare is continuing. Now we don't have even only virtual machines, now we have containers, and that is a concept which everybody thinks is brilliantly and new, but with CH root, we had this already in 2005, but in 2005, but now we are containers, and my guest book is running in the container. Now I get 1, 2, 3, 4, 5 layers. Thank you very much, 2 more layers, and more containers, and of course here again, the containerization software behind, might be OpenShift or something else, Docker. Now again, we can separate this all, but think about the elasticity, the point which we would like to have everything as agile and dynamic as possible, so we can make maximum use of resources. If you have a dedicated cluster, there will be automatically some CPU cores which are unused because there's not the demand for this. And then you also need to have a good assessment of your demand so that you do not overscale your cluster too much, because then you get dormant resources, but you also cannot underscale your cluster too much, because then you are running into something like a denial of service. You're getting too many requests which you cannot serve. And there's one more guest book, and there are other applications and so on. You see my nightmare starting. So here we are again. Let's do networking. The ideal network stack now needs to have for each of my layers one network. Okay, if you throw money at the problem, I can do. I got a management network for IPMI and the PMC. I have a provisioning network where I can push in containers, push in virtual machines through the hypervisor, and the hypervisor then itself distributing the virtual machine to its right, assigning the virtual machine to the right core, the right CPU core, and then the things are running. Okay, yeah, that is, looks fine, looks good. Then there's the intranet. You would like to make your guestbook visible to everybody on site. There you go, internet connectivity. But hold on. There might be some students and others which would like to have also access to those web pages. So now we're starting with first security, to expose some services to the internet. Yes, we're doing this since decades, and we put a firewall in between, and this is established technology. So yeah, there it goes, a firewall. Can have it, not a big problem for security. And then we get other applications, maybe running on the same hypervisor, which are used for the operational or for the OT network, for the industrial networks, and they might run in the same hypervisor. But I have them on the same network, and at CERN it's exactly like this. We have a dedicated industrial network for all our control systems. Technically, we got even several networks. We got network segregation, physical network segregation in place. So the accelerator is served by one network, and each of the experiments are served by their own industrial network. But hold on. Some of the critical services are now exposed via the same hypervisor. So, and there might be even some critical services on the control systems which you would like to expose to the intranet. Think of my engineers. They would like to monitor the control system status of the accelerator from the office. Yes, now we can invest in heavy cabling and having at each office 2 outlets and 2 computers, one for the OT network, one for the IT network. But apart, if you're working in military or working for the government where you have critical networks and full network segregation, who can afford that? At least I can't. So there we are. We need to have another firewall bridging from the control network to the intranet so that people can log into the control system from the office to do some easy controls and maybe even changing some parameters. Whereas for CERN, lots and lots of the equipment we're running an accelerator is being produced outside CERN. Take Triumph again, should be proud of that one. It's a brilliant site, I love it. I love Vancouver myself, so I've never been to your place, but Vancouver is lovely. There might be some physicists, some technicians, some engineers sitting in Vancouver Triumph who have contributed to running the LHC or still contributing to running the LHC. And sometimes it's much, much easier just dropping them a message saying, look here, can you look at your system? Here, it's looking the power converter looks a little bit odd. I think it's starting breaking down, or can you readjust it? And then we can say, yes, let's stop everything, fly the guy in from Vancouver, takes 24 hours, let him do his repair and checking. Much easier for remote diagnostics. And if you look at control system outside in industry, nowadays you might run some equipment from Honeywell or from Siemens or from others. Their experts would like to have remote access from wherever their offices are, because for the first diagnostic, it's much more cost efficient to have remote connection. So there we go, my nightmare is starting. Then, of course, we talked about containers and hypervisors. Now with this assembly I draw here, with having no full separation of computing clusters, we have now a second breach apart from the network. I can now, if I break into the virtualization system, into the hypervisor, if I break into OpenShift for the containerization, now I can technically jump from the intranet to the OT network. So I got the next security problem there. Yes, I can duplicate everything, but we'll figure out that duplication might not help you. Because there's first a network management system in place, which is doing the domain name service, maybe static or dynamic HCP. You would like to give it some timings, you get some NTP service and so on. You can duplicate them, having them for the management network, for the provisioning network, for the intranet, and for the industrial network. But who is doing this? Duplicating this infrastructure, this is starting getting very costly. And you would like to synchronize your DNS records should be the same overall. So they need to talk to each other somewhere. NTP needs to get the same time signal. Of course, you can set up 4 NTP servers, and each of them have their antenna to get the GPS signal there. But are you doing this? So now we have a common service, which is maybe even bridging the networks. But as I said, if you do duplication, then you have a primary and replica, which need to synchronize. And the synchronization, again, is a bridge, unless you have really strict silos where no interconnection is happening. and my nightmare is continuing. Doing provisioning. Now you would like to pump in your virtual machine. So first you would like to administer the hardware, and you do this remotely nowadays. You would like to do a telnet or more an SSH into the IPMI interface. You need to have an admin console. Fine, I put an admin console in each of the offices of my administrators. And they have a second admin console for those ones who are now doing provisioning, because installing a virtual machine, that is more or less generated by Puppet or by Docker or by similar tools, which are the library of all the different container options which you got, all the different operating system options you got, all the different modules, manifestos, which you can integrate into your operating system. So you need to have some orchestration. Puppet and Docker are yours. Yep, I'm still working, but now for convenience, my administrator do not want to have two consoles. They would like to have one console, because sometimes they need to copy paste code back and forth between the two sides. So convenience versus security, instead of having two consoles on the desk, they just have one. Having just one console on the desk is bridging my management and my provisioning network. So I put everything into a demilitarized zone, but now that one might be even used for this zone itself needs to have admin access. So I have another bridge from my intranet into the DMZ, so the administrators can manage the DMZ in itself. So put this on a separated network segment. Okay, we can do, here's my DMZ. I need to put more my DMZ. Now we fill it up. For example, I would like to have a single sign-on, one account, one password for OT, for internet, for programming and so on, eventually augmented by multi-factor authentication. Definitely would like to have one LDAP in Active Directory, because I do not want to fiddle around with lots of users which are not synchronized. Yeah, there should be Stefan, there should be just one account for Stefan. There's only one Stefan at CERN, so the information should be visible on the controls network, on the provision network, on the intranet, and so on. And then look at all your containers. They must be stored somewhere in a storage system and databases. So now I need to also have the storage system and the databases being connected to the provision network. Still, this works because everything here is more or less connected to the provisioning system. But did we get all dependencies? Today it's a single sign-on Active Directory LDAP. Today it's OpenShift. Tomorrow it might be Kubeflow or whatever else. So it's dynamic. So that's very agile. You need to really keep pace with your DMZ to have all your dependencies inside this DMZ. And then we come to the future, or not even anymore. Lots of people are doing development now on Git, using Oracle databases, using Jira, and they are asking, they are hosted on the internet. They're hosted on the internet, both together, one or the other. Oracle is trying to push us to not have the databases anymore on CERN side, but using Oracle clouds. We are being pushed now away from our blobs here onto the internet. If you're doing programming, you might use tools like PyPy NPM, which are automatically pulling in from the internet libraries and packages into your software development environment. Some people are even look for containers. I need to have a WordPress web server. Oh, here, found a container. Oh, here is a virtual machine. Download it. Downloading doesn't cost anything nowadays anymore. And then you run a full-blown container from a source which you do not control. PyPy is pulling it from wherever it's pulling on the internet. And the containers, ask your developers where your software is coming from. Or if you're doing your own software development, do you know from which different internet sources did you copy all your code? Question mark. Would love to see somebody really having an inventory there. So how to securely import external packages and libraries? At the moment, we are pulling it from the internet. It makes it through our firewall onto the intranet, and then via some other means into the database and the storage system to be provisioned via Docker Puppet into my computer center. You see how it's getting complex. And what we said about complexity is killing security. And then we get monitoring. We would like to see the status of our whole system. So is my hypervisor up and running? Is my virtual machine not overloaded and properly running whatever the containers? But also the hardware. We like to ping the hardware, doing a small trace route into the hardware every second, seeing is the hardware still up and running. But now, shall I run the monitoring on my provisioning network where it belongs to? Should I run my monitoring on the management network where it might belong to? Should I have two, or should I bridge the network? So now my management and provision network is already bridged Was bridged before by the admin console. Now it's even bridged again via the monitoring, because monitoring can be lots of information. We're running a huge Elasticsearch cluster with all our monitoring information, which is containing hundreds of terabytes of data. We can't clone this easily, but we come to more. So, oh, sorry. And then, just to finish this up, your databases themselves are also running in your computer center. So now you introduce a loop. The databases will run in your computer center using and benefiting from the same infrastructure. Your Puppet service might run in the computer center as a container or as a virtual system somewhere in the computer center. Your monitoring, Elasticsearch, is using the storage of your computer center. So here we are. You see the complexity of the overall. If you now see how you take your knife and chop in my network in such a way that I have a clear purpose computer center, I would love to know. So here's my summary for your nightmares, and I hope you don't get them. This got damn complex, complicated, convoluted. I hope you agree on that one. The risks are my hypervisors, my container platforms, and everything similar, even if they are supposed to serve different networks, can be used to bypass the firewalling. We have seen in the past that VMware got compromised, VMware got vulnerabilities where you can break out of your virtual machine. Same for Hyper-V, same for OpenStack. There might be some vulnerabilities where you just creep out your local virtual machine, which might be controlled by an adversary and attacker, and then you use your channel via the hypervisor and attack more virtual machines. Then we got multi-purpose applications. I tried to explain to you that we got gas spokes visible to the industrial network, to the internet, to our users. Ideally, I would like to separate them and have tight firewalling. But if I run a hypervisor, next to your virtual machine might be a financial application, close to an application running Mathematica, close to an application which is running WinCCOA of Siemens, a control system, and next to a database which belongs to an HR person. So you see, multi-purpose application for elasticity and agility, everything is more or less put together. We need to have even tighter firewalling for high-risk networks. So what we are doing is putting proxies and gateway in place, even thinking of data diodes. But if your computer center is as such as I described, unless you have a fully separated computer center, this doesn't fly. The same for common services. Even if you have two different computer centers fully separated, you would like to synchronize your LDAP and Active Directory. You would like to synchronize your Puppet manifestos for installation. You would like to synchronize your Linux or Windows installation bases. You would like to synchronize certain databases and so on. So those common services are bridging different networks. So we got a DMZ. At CERN, our main data center is considered to be the DMZ because it's containing all the services I'm mentioning here. DNS, DHCP, Puppet, containerization, databases, storage, everything is served from the computer center. So it's a growing and too big DMZ. And last but not least, cacophony of dependencies. It's very agile. In the past, we had 3 layers with an operating system and application. Then the virtualization came in, and the moment where I thought we have now OpenStack completely under control and well secured, some guy came in and said, look here, we got here Docker containers. That is the new virtualization. Let's do containers on top of that. Oh, brilliant. Next layer I have to secure. And now it's even one step I didn't put in this presentation here. Now the people come to something which they think really clever, because hypervisors and containers, they introduce overhead to the hardware. Now we can run also applications on something they call bare metal. Now we're back to the beginning of the 21st century, where we now back to the operating system there. But this bare metal is now looking completely different than it was looking 20 years ago. So it's quickly changing and adding more and more complexity. And then we got the external cloud services I mentioned. What if Oracle is forcing me with my database into the cloud? Another dependency, another layer. Git already we synchronize Git with our on-prem GitLab instance, so we control a little bit of the software, but more and more cloud services, Jira, Atlassian, they might think that everything will be served from their personal cloud or from their public cloud in the future. This is what might just happen. And then we spoke about software dependencies, PyPy, GitHub, NPM, and how do you curate this? So the solution, show me. I'm open for any suggestions. And with this, I'm done. Thank you very much. Other questions?
Well, thank you very much again, Dr. Lüders. This is just as informative as I thought it would be. Yes, I believe we have a number of questions. Okay, looks like Jazid is already jumping in with raising his hand here. But first, I'd like everyone to give a round of applause here to Dr. Lüders. All right. Okay, I'm trying to go back here and through the chat here.
Shall I go through the chat?
Yes. Yes.
You mind? So I just pick those ones, the comments which I think are worth a comment from my side. So yes, CERN is an independent international entity like the UN. We are not part of the UN system, but people like me working for the organization have diplomatic immunity in Switzerland and France. If you want to enter CERN site, you're leaving Switzerland or you're leaving France and you're entering, like in New York, you're entering international territory, which means that if the police wants to come on CERN site, they need to be invited by our host relation office, which we definitely do. If they have a need to come on site, they're always welcome. But we have our own regulations. We are not bound to Swiss nor to French law, which does mean that we are something like how you say that's Wild West. We're following either law to the most strictest, in particular to personal safety. We follow the most strict law in France, Switzerland, or in Europe. So yes, so it's like the Vatican, yeah, maybe like the Vatican, like the UN, but we don't have any UN representation. Are all the CERN web pages useful? Who goes through all the 1.5 million pages? Lots of them are papers and documentation, plots and physics results, which are stored on web pages. So this is where people more or less drop their papers, and this is what the 1.5 million web pages are. If you want to build your own accelerator, for example, there's a system called edms.cern.ch. All our engineering documents are stored there, and most of them are public. So if you want to build your own accelerator, just be my guest, download the documentation. If something missing, contact me. You just need to come with the proper funding. An accelerator like the LHC costs between $5 and $10 billion. I think it doesn't matter if it's now US or Canadian dollars, it's money. But if you got the money, I'm pretty sure you got the space. 27 kilometers. I think this you find easily somewhere in the outback of Canada. So, but there you go. We're not a country, no, we are. But yeah, as it has been said there. So. Yes, Shazad, you're right. Cybersecurity is CIA. That is definitely another approach which you can take: confidentiality, and credit, integrity, of availability. But underlying, you get still the hardware, and networking is part of the fact to guarantee your integrity and the availability and also the confidentiality. Also, are vendors like Siemens and Microsoft always sending quality updates to CERN? Oh, that is a question. What do you mean with quality updates? No, we're getting the same shit everybody else is getting. So sometimes you're getting vulnerable software. That's one of the paradox of software development. There are two products worldwide where me as the company has to bear the consequences for a bad product. So we have to invest in all those networking, segregation, and security and IDS and so on. Why? Because we're buying products which are not secure by the beginning. Think you buy a car and the brake is not working. Yeah, you can sue BMW that the brake didn't work or the airbag didn't deploy. But for software, that is with me. I have to pay for the updates and for the security. You know what the second product is, where the end users have to cope with the cost of an unfinished product or for a vulnerable product or product which is not working. Somebody, an idea? Drugs.
Get away. Yeah.
If you go drugs, cocaine, you buy your cocaine with your favorite cocaine dealer. I'm not saying that you should do, but if you would buy cocaine, no guarantee that it's working. So there we are. Private cloud with OpenStack, yeah, why not? Maybe we talk later why that question. We're running our own OpenStack instance, the full software stack of OpenStack. We're part of the OpenStack Foundation, where we're contributing with software, and we're benefiting from this foundation together. So we are all self-sufficient to a certain level. Yes, we try to be, but of course there are external dependencies, and the grid, of course, also we got external dependencies because we need to have the computing power of the worldwide grid to process all the data we cannot do in our computer center ourselves. Environmental standards, no, we have environmental standards being given by the European Union and by Switzerland, which we are following to our best. And yes, we try to be as energy efficient as we can, and also as much environment and ecologically friendly as we can. So there are lots and lots of studies going on in that area, how we can still improve. Is there any literature how CERN people work together? Indeed, I think there is. There were some people writing books about this one. I cannot link you to any. I have to check the CERN library, but there were some journalists, some psychologists going around and looking how international organizations like CERN are working. There's another international organization which is called ITER, doing fusion reactor research, and most of their way the international collaboration has been set up for them has been copy-pasted from CERN, because it's a working international organization. And in those bad times we're living in, still CERN is international. We still have collaborators on site, which coming from countries which some people might think those people should be banned. CERN still thinks the same thing. We are thinking of banning the countries, and we do banning the countries and their contributions to CERN. But if it's coming down to people, they are physicists which are living in the area, and there is no need to ban those people unless they really take position for one or the other side in a war. And if this is then in contradiction with the code of conduct of CERN, then of course they don't have any being anymore within working for the organization. Solution: give every CERN member Raspberry Pi 4 if you can find any. Yeah, that is a nice one, but I think that won't fly. So yes, AA manager, AA will solve everything. You're completely right, AC. That is the next buzzword on the market. I was working on neural network, but I think nobody cares about it. It's called neural network now. It's artificial intelligence, and I would like to see an AI solving that problem. Yes. Mathematica, we provide Mathematica as installation on-prem on-prem servers. So Mathematica is also in the cloud. You can have both of them. And last but not least, is the Windows subsystem being used at CERN? Not sure what you're meaning. We are still having lots of Windows servers running in the computer center, which are managed on site, so server to 16 or higher. We got also Windows desktop installations. But yes, there are some thoughts to move in this Windows 365 cloud because of cost efficiency.
I think she might be referring to the Windows subsystem, which is the Linux installation that can be run under as a like virtual machine under Windows.
Oh, Mary, now you're thinking I'm a technical guy. I'm a physicist. I have no clue what you're talking about. So I cannot go beyond the knowledge I shared here in this presentation. No, I don't know. I don't know. I literally even don't completely grasp your question because that is not my main turf. So I can answer this to you if I can get back to one of my experts. But so far I know Linux is running on Linux and Windows is running Windows, and only on end devices you might have some virtualization where your laptop is running some kind of a virtual environment where you would like to spawn up a Windows machine. But apart from this, yes, sorry, Windows can of course run on OpenStack. This is what we do. Still, I think I'm floating around a little bit about the question and the answer, so I'm not sure if I answered anything in that area there. Sorry.
And maybe now we could jump to Shazad, who's had his hand up so patiently this entire time.
Oh, sorry.
Hello, hi, this is Shazad. Can you hear me?
We can.
I can.
Yeah, I am presently based in Pakistan. I am an EIT of the APGSSK Canada. My question was regarding, like, we are talking about cloud and Dockers, these days, even the companies are happy since it has reduced their OPEX and CAPEX, but it comes with a trade-off. Like at the end of the day, though, you have the firewalls and all the protections and the VPNs, but still you are over the internet, and the adversaries and the hackers, they can still manage to seep in. So it has basically increased the role of the SOC, the Security Operations Center. You need to have a SOC, so even you are paying for that. So what would you suggest? Like, is it good to keep your confidential or important stuff? Like, I am being a telco guy, and people talking over the phones, and there is a possibility that someone can listen to them. So what would you say, that some things should still be kept on-prem or switching to cloud is better?
So that's my main problem I have with moving the cloud. And yes, we are moving partially into the cloud. So until now, my computer center was on-prem. I got my my private cloud, I got my public cloud for exposing to the internet, and I got my own SOC on CERN premises, which will still there. We're running an open stack, we're running an open source SOC based on Kafka, Elasticsearch, malware information sharing platform, MISP, Pro IDS as intrusion detection system, and lots and lots of glue in between, which is able to digest something like 3 to 5 terabytes of data a day, and we're analyzing this automatically and issuing then alerts to the end users, depending what we find. So, and we're holding some one petabyte of security data on-prem at the moment. Going to the cloud, first thing, just going to the cloud and ticking a box saying, look here, now you're in the cloud, that's far away from this. So the migration costs are non-negligible. And we are now looking how we can use the information given by Sentinel and Microsoft Cloud, how we can push this back into our SOC on-prem, having a copy of all the log data on-prem and can analyze this. So we're looking into some kind of a hybrid of using partially the security functionality of Microsoft Azure, plus still our main SOC on CERN side. Is this giving you some kind of an answer? There's lots of reviews going on. So even the setup of Microsoft, to have it set up in a secure fashion, we're still investigating how we can make the maximum out of this. And we have found some areas where we think there's still some room for improvement. Thumbs up, down. Is this answering your question?
Yeah, thanks to some extent, or rather to a larger extent. Thanks.
Okay, welcome. Why isn't CERN instead doing proton-antiproton collisions? Wouldn't that boost the available energy? That is a very good question, but accumulating vast quantities of antiprotons, this is what's done in Tevatron, was done in Tevatron in Chicago. That is a challenge in itself. With protons, proton, that would be the first area we can have the maximum intensity in the beams. So I'm even not sure if that would boost the available energy, because then you just get annihilation between the quarks. So yeah, nope, I don't have a good answer to that one. I'm too far away from my physics classes, which already some while ago.
Wouldn't there also be issues in trying to generate that vast quantity of antiprotons?
Oh, we do create antiprotons on quantities. So Tevatron in Chicago Fermilab has shown that this is feasible. We produce also antiprotons, but we use them in other accelerators and not in the LHC. So if you want to boost the energy, you can take ions. This is what we're doing once a month, once a year for a month. We're taking lead ions, which are of course a factor 82 more heavy than protons. And if you collide them, then you get more energy for the buck. But it's also getting more dirty because you do not know what really collided. So that's why there's always an interaction. Ideally, you take electron-positron, so electron anti-electron, because if they collide, they annihilate. They really annihilate to zero, to energy. Sorry, to pure energy. While proton-proton, you have some quarks colliding with some quarks or some gluons, which are constituencies in the proton. They collide together, but you do not know actually what is colliding. So you get some uncertainty in there, and you do not have pure energy on the spot, but you got some energy distribution, which depends on how did the quarks wobble inside the protons. And for antiproton-proton collision, I would even think it's somehow similar. But yeah, I don't have a good answer to that one, AC. I'm sorry. And yes, Mary, IBM also provide cloud services. There are lots of cloud service providers because this is where the market is going. But I'm not convinced that that is always the most cost-efficient way to go. For pure compute, for example, this Instagram for the physicist, this is where we're looking into cloud services. So just giving them some LHC data to crunch the numbers, that is easily what we can do. In principle, we just take our virtual machines used for number crunching in the worldwide LHC computing grid, and then you tweak the virtual machines so you can run them in a computer center of IBM or of Azure or of Amazon or wherever else you want to do it. So that's what we're testing. About cost efficiency, again, you have to look you have to see. So if you're looking for opportunistic resources in Amazon, for example, that might be cost efficient. Compute is not that expensive. What is getting expensive is storage. Storage is more expensive, and the network traffic is also expensive. So if you have something where you have a really high throughput of traffic going back from CERN to a cloud service and back, this is what you're paying. So people always think it's in the cloud. I'm not saying you do, but if you look at the contract, sometimes it's really getting nasty. So just looking in Microsoft, not blaming on Microsoft here, but the negotiations to move our mail system into the cloud. It's going something like, how many mailboxes do you have? But we have more mail addresses than mailboxes because sometimes they are aliases. So how many mail aliases do you have? How many human bodies do you have on site? How many accounts do you have? So take human bodies, there are 15,000. How many accounts? There are 40,000 because I can own several accounts. Then I can have for each of the account one mailbox, but I can have aliases to the same mailbox. And then there are mailing lists and there are forwards and so on. So I'm looking at how the license scheme and how the costs were then calculated. This is something like cooking a soup, where it's not straight from a catalog where you go to a McDonald's and say, look here, take one big Mac, you pay 5. You take 2, you get 10. It's more like you want to have a Big Mac. Yes, you have to also think how many cheese do you need and how many bread and salad and tomatoes and mix this together, and we give you a number, but we can't give you a clear number. So it's I was a little bit disappointed how this number has been calculated. But maybe I shouldn't be so frank here. Web apps, portal apps, and an internal app package manager. Maybe not solution for CERN. Isn't Puppet something like this? We're using WSUS. Yeah, I'm struggling what you mean. We got our own RPM distribution software for Linux installation. So that is there. So clouds are not per se impractical, but you need to have really a focused, targeted application, and you need to have a user community which is willing and properly matching to this one. So Microsoft, for example, using Azure, if you are a pharmaceutical company and you have only Windows desktops in your offices, that might be something working. But apart from this, for CERN, it's a little bit more complicated. Yeah, no, Windows is, we are more a Linux shop anyhow. So we are now mentioning Windows because some part of the office, of the user community in the offices in finance and secretariats and HR are using Windows. If you look at the physicists, they are more the Mac Linux user community. Some awkward silence here.
Oh, it looks like maybe the questions are winding down now. And perhaps the lunchtime is as well. So on that note, perhaps I will end the session. But first of all, I'd like to give Dr. Lüders another round of applause here. And so I bid you all.
Just one more comment. Sorry, Juniper. Just one more comment. Since I now understand the question, like maybe a proprietary Google Chrome. Yeah, we tried to. Sorry, now I get the question, Mary. I'm sorry that it took a little bit of time. So no, we're not developing our own web browser. I think that is not the core business of CERN. But for example, since we are not wanted to go and continue with Skype, but also there are not too many alternatives. We developed our own CERN phone application for Androids and iOS system, so we can have telephony based on data instead of normal telephony. So there we developed ourselves. But again, that is the problem we are all finding. Do you do your in-house development? Then you don't have all the compatibility which you're getting. If you're going to Microsoft, and still using Microsoft, but take Google, you get all the integration in the Google environment. That's in their interest because this is how they want to get the buy-in, so you're getting your lock-in. But if you want to keep out of that, then you would like to have solutions which you can replace easily, which you need to develop yourself. So instead of using WhatsApp, we're using Mattermost, which is an open source solution for chat. But that is developed, it's not developed at CERN, it's used and run at CERN. But now you need to integrate it with other things. So starting now to integrate everything, this is what you're getting for free. And also looking at mail, Google has how many hundreds or thousands of people just doing one application, Google Mail. The CERN Mail team is hardly 10 people. I think it's even less than 10 people. So you can't even develop such things yourself because you don't have all the resources. And that is, I think, the challenge we all are facing. The internet, there are lots of services bubbling up. You monitor this, you see what's coming up. Zoom, for example, and then you get a choice. Do you do your development of Zoom yourself, so you have your own house solution being independent, or do you engage with Zoom? If you engage with Zoom, you are locked with them, at least for a time, by contract. If you develop yourself, you will take it out. You will be 1 year late anyhow, and maybe your people, your constituency will move already to Zoom in any case, because they would like to have a solution now, and developing something will take a year. That's natural. So you're always behind. So we are really in a bad situation if you provide IT services. You need to have the SAT AI to predict more or less what are the big new things which we should develop in the future, so we can serve our users well. So there we are. So this is why we're taking GitLab. This is something we can run locally, but still using community. We're using Red Hat Enterprise Software and CentOS, which is open source, and we're paying for services and so on. So I'm more the fan of open source, but sometimes you need to buy, and Mathematica or Oracle, those are very brilliant applications, very brilliant databases. You just can't get out of them without using anything else. Now, of course, there are alternatives, but alternatives not always solve all your problems.
Oh, you mentioned Red Hat and CentOS Linux there. I mean, until a few years ago, there was Scientific Linux, which was based off that and tweaked by a number of labs around the world as kind of an international collaboration, but that sort of petered out itself too. That sort of thing could happen.
Indeed, indeed. Until SLC6 or SL6, which was managed at Fermilab and at CERN in parallel, so the SL6, Scientific Linux 6, and Scientific Linux CERN 6. This was intended to keep the software stack stable. That is a requirement which moved more out. And then, of course, maintaining this is not something you can maintain for free. You need to put manpower at this one. And in times resources are scarce, you have to think where you can benefit from other things. So we moved to CentOS, which was a very good call at the time. But then Red Hat decided to have this CentOS stream where the packages are more or less permanently pushed in, which is still working in certain environments. But if you have a control system, or if you have a farm of computers doing compute, that is something you do not necessarily want, because you do not control the update cycle anymore, and you might run into some compatibility problems. So yeah, CentOS is good as such. The decision to CentOS stream, we can discuss this longer, whether this has the wanted impact on it.